physical modeling. So today we're going to talk about the simulated bow. So obviously here we are in the city of the violin, so I think that the topic is appropriate. So we're going to review a bit of the physics of bow motion, and then the core of today's talk is going to be, well, I'm going to try to give you tips and tricks for the design of fast and reliable numerical schemes. So I don't know if any of you is into physical modeling or if you know what that is, but essentially physical modeling is the design of physical equations, mathematical equations that describe the propagation of sound in musical instruments, and the design of computer methods in order to simulate these systems. What we're going to try to do today is simulating this kind of motion. So this is a very nice video I found on YouTube, and essentially the whole point is to understand the physics of stick slip. So I have a graph here. You can see eta is the relative velocity between the bow and the string at the bowing point. So you see from the video that sometimes the string is attached to the bow, so the bow and the string move with the same speed, but then all of a sudden the string starts slipping across the bow. So if you plot the relative velocity over time, you have a sticking phase where the relative velocity is nearly zero, but then you have these peaks which correspond to the slipping phase where you have a sudden jump velocity and the string starts sliding across the bow. So the stick slip motion is essentially motion that is driven by friction. So I don't know how many of you have taken first year physics degree classes at universities. Well, Sebastian has. But basically, you know, they teach you that the friction force is proportional to the downward force, in this case Fp, which is the pressure of the bow on the string, times a friction coefficient. So that's all you need to know when you're solving your first year physics degree problem. You have a mass sliding on an inclined plane, and you just assume that the friction force is just proportional to the normal force to the surface times the friction coefficient. So the bow works exactly in the same way. So Fb is the downward pressure force, and phi is the dynamic friction coefficient. That is a function of the relative velocity between the string and the bow. So when you're solving your easy first year physics degree problems, you always assume that phi is a constant. So that doesn't change with the relative speed, and that's how you're able to do all your analytic calculations and solve all these easy problems. But for the string, actually finding a form for phi is pretty complicated because nobody really knows what the form of this friction coefficient should be. So this is an ongoing problem, and people are still studying that, and they're trying to come up with questions.
Yes, the force, it's not as Brachian displacement in the bow. It's not the same along the bow length. When you're closer to the frog or the tip.
Sure. I mean, this Fb, it is just basically an input parameter. So I'm assuming that the bow is acting just on a point of the string. So you're not moving the bow along the string now. So we're just like considering the bow as being fixed at one point along the string. And we are also assuming that the string is only moving in one plane. So it is a very simplified problem. So the bow doesn't make an angle, it's just pushing vertically and sliding. Okay, so Fb is the amount of force that the bow is exerting vertically, and eta is the relative velocity between the string and the bow in this direction. So it's a very simplified model to start with, but you know, we need to start with like very simple problems and then perhaps move on to more complicated scenarios. But essentially, yeah, you see there are here at least 4 different versions of this friction coefficient. So panel A is your Coulomb drive friction, which is the friction that you use in your easy first year physics degree problems. It is constant. It only changes time with the relative velocity because friction is always opposed to velocity. But that's basically the easiest kind of friction coefficient that you can think of. But actually that turns out to be not very good for Boeing, so that's why people started investigating different possibilities. So in panel B, there is this so-called classical curve by Woodhouse and Smith from 2000. They actually ran experiments. They put the mass onto a conveyor belt, and they coated the mass with rosin, and they basically measured the friction force from this experiment. And they came up with, a mathematical formula, and the graph is represented in panel B. That curve works to some extent, but it doesn't work to some other extent, and that's why people investigated different possibilities. So there is an even further work by Galuzzo from 2017, and he also ran some experiments, and he put in some, I don't know, mathematical thinking, I guess, and he came up with the curve in figure C. Then other options are available. For example, Bilbao, who was my teacher in Edinburgh, he worked a lot on both string motion, and he came up with his own version of the friction coefficient, this time based exclusively on mathematical assumptions. And that is actually the form of the friction coefficient that we're going to use today, but there is no reason not to use the others. So just for the sake of doing a demo, today we're going to use this particular form of the friction coefficient, but all I'm going to say today is directly applicable to all these other friction coefficients as well. The most important property of all these curves is that the sign of phi is the same as the sign of eta. So if eta is positive, phi is positive, and if eta is negative, phi is negative. And we call this property sector boundedness. And this property is really important because, like I said earlier, friction dissipates energy, so necessarily the friction coefficient has to have the same sign as the relative velocity, because that's the condition that you need in order to get dissipation. So today we're going to talk about the bowing mechanism, but we're going to start from a very simple system, which is the mass spring, so the harmonic oscillator. So we're going to bow a harmonic oscillator, and we're going to try to figure out things from this very simple system. I don't know why this isn't working. Then we're going to use that simple system in order to compare a bunch of time-stepping routines. So remember that the core of today's talk is to teach you how to construct finite difference schemes that you can use to simulate the bowing mechanism using a computer. So we're going to use this very simple system in order to understand how to build the finite difference schemes. And then we're going to move to the musical case of the bow string, which is actually what we want in order to make sound synthesis. But because we have already done all the work on the harmonic oscillator, we will be able to move to the more complicated case of the string pretty easily. So now we start with the equations. There will be a lot of them, but hopefully, you will be able to figure out like the most important concepts. How many of you are familiar with the harmonic oscillator? Some people. Physics degree or mechanical engineering? Okay, cool. So for those of you who are familiar with the harmonic oscillator, that is basically, just a spring connected to a mass. And if you write the equations using Newton's law, then Newton tells you that the acceleration, or the force, in this case, minus omega naught squared u, is proportional to mass times acceleration. So here it is just Newton's law for the harmonic oscillator, and this part is the linear part. But then you have the extra force, which is the friction force coming from the bow. So you need to augment the harmonic oscillator with this extra frictional force, which, as we have seen a couple of slides ago, it is just proportional to the downward pressure Fb times the friction coefficient. And the friction coefficient is a function of the relative velocity, which is defined as the velocity of the mass minus the velocity of the bow. Okay? So in these equations, you have two input parameters, which are the velocity of the bow and the pressure of the bow. And then u of t is the displacement that you need to compute, so it is unknown, and you want to be able to calculate u, or better, to know how u evolves over time. And omega naught is just the ratio of the stiffness of the spring and the mass, okay? So this is how you set up the equation of motion, really, really simple. Okay, there is a very important concept that I want you to understand from today's talk, which is the concept of passivity. Why is this system well-defined? It is well-defined because it is passive. That means that the way we set up the equations is such that we know that the system dissipates energy over time. So if you stop moving the bow, so you're not injecting any energy into the system, then you want to make sure that the mass sliding on the bow is actually dissipating energy over time. How do you compute the energy balance? There is a very simple trick, which is the trick that I always teach my students as well during my acoustics course, which is to multiply the equation of motion by the velocity. So you multiply the original equation by the u dt, and then you use very simple identities, and you actually can derive the rate of change of the energy over time. So the energy is just the sum of the kinetic part plus the potential part, which is the energy of the harmonic oscillator. And the time derivative of the energy, you see, is negative Fv times the u dt times phi of the u dt. And this is necessarily negative because of the sector-bounded property of phi that we saw a couple of slides ago. So we say that this system is passive, meaning that the bow is dissipating energy. And that's a very important property that we will have to replicate in the discrete time case. So bear that in mind. But, this equation works fine, but, that's how Isaac Newton would set up the equation. He would say, okay, force equals mass times acceleration. So, you have an equation which is defined as the second time derivative of the displacement. But if you come from a different background, in most cases, you want to define the system as a first ordering time system. So that depends only on d dt. So in order to do that, you can recast the same system in first order form. So you define a generalized coordinate and momentum, q, which is equal to omega naught u, and p, which is the velocity, the u dt. You recompute the form of the energy, which is now given just by the sum of the squares of q and p. And then you can rewrite the same system as before in first order form. Except that now x, which is called your state vector, is now a vector, it's not a scalar anymore. And the vector has two components. One is q, which is the generalized coordinate, and the second component is p, which is the velocity. So by doing this trick, you're able to move from a single scalar equation, which is second order in time, to a vector equation, which is first order in time. But the system is just the same, so nothing changes. It's just like a different way of writing the same equation. The most important part of this system is the form of the matrix J, which is Q-symmetric, meaning that the elements on the diagonal are 0 and the elements on the anti-diagonal are the same but opposite in sign. And the gradient of the energy in this case is just x, because it's just the partial derivative with respect to q and the partial derivative with respect to p. And since the energy is just the sum of the squares, then the gradient of the energy is just x. And you want to check passivity on this system too. And in order to do that, you do the same trick as before. So you multiply by, in this case, the state vector, the transpose of the state vector. And you can run, you can just do identities, and out of the fact that J is an antisymmetric matrix, again, you have the property that the energy defined as a function of the state vector now is decaying. So regardless of the fact that you use the Newton version of the equation of motion or the first order in time equation, you end up having the same thing. Nothing changes. You're just recasting the same system in a different form. So you can switch back and forth between the two systems. But when we move to discrete time, you will see that things can be very different, actually. Because when we write finite difference schemes in order to integrate these equations over time, we will run into a multitude of possibilities. And it will turn out that some forms are actually, I don't know, better than others in order to write more efficient and more reliable schemes. So this is the reason why I introduced to you the equations into different forms, because we're going to use both forms in discrete time in order to update the solutions. So what are we looking for when we write simulations? We're looking for stable simulations, because supposedly we're writing a real-time version of this bow string, so you want to make sure that the string doesn't explode when you're running your numerical schemes. But then, of course, you're also looking to have efficient schemes because, again, for the same reason, you want to run these simulations in real time. So you want to make sure that they run in the least amount of time possible. So we can now move to discrete time. Is any of you familiar with the concept of finite differences? No? Okay, so, well, this is a first then. But, finite differences are very easy actually. So, this is your arrow of time.
It's not very clear to
Oh, you can see it? Can you see it from the computer?
The computer, yes.
Okay. Well, there is not much I can do about it, I guess. Well, there is an arrow here, which is the arrow of time. And when you move to discrete time, you use a sample rate. So usually its audio rate is 44.1 kilohertz. That's the sample rate you have, in digital audio usually, So that means that you're now considering discrete time, which is defined on a grid of points. So these little squares here are the grid of points, and they're all labeled by an index n. So n is 0, 1, 2, that defines the time index. And the distance in time between two grid points is exactly k, which is the time step, or the inverse of the sample rate. So finite differences are used in order to find an approximation to the true solution x of t. So x of t is unknown, you don't know what it is. You have a differential equation that describes how x evolves over time, but in most cases you don't know an analytic solution for x, so that's why you resort to finite differences in order to find an approximate solution to x. So the approximate solution is called xn. N here is not an exponent, it is just an index that defines the time index precisely. And you see that the true solution x has got this continuous shape, and the approximate solution xn is sort of not exactly on x. So there is an error that is defined at each time step, which is itself a time series. So the error is just defined as the difference between the approximate solution xn minus the true solution at the time tn. Okay? So that's the definition of your error. So unfortunately, people here cannot really see the colors for some reason. But if you're connected from home, you can see all these different definitions of the difference operators. First of all, you have time difference operators, and they're all acting on the time series xn. So there are a bunch of them that basically approximate the first time derivative, dt. So there is delta minus that takes into account the current time step and the previous one. Delta plus, which takes into account the current time step and the next one. And then delta dot, which is a centered difference, which takes into account the the next time step and the previous one. And these are all approximations to the first time derivative. But you see, they also have a different order of accuracy because some operators are only first order accurate, since the truncation error is proportional to k. But then the standard difference is second order accurate because it is the truncation error is proportional to k squared. But then you also need an approximation to the second time derivative if you're trying to solve Newton's law. And again, you have a stencil here and you have your coefficients. And this particular approximation is second order accurate because the local truncation error is proportional to k squared. So these are just definitions, nothing complicated. Okay? These are difference operators acting on the time series, and you just apply the definitions. You have averaging operators as well. In this case, approximating unity. So these are not approximating differential operators, they're just approximating basically the identity. And these are also very useful when you're constructing finite difference schemes. So the notation is very similar, so I have mu minus, mu plus, mu dot, and mu 2. And again, mu minus means that we're considering the current time step and the previous one. Mu plus, that means that we are considering the current time step and the next one. Mu dot means that we're considering a centered approximation. And mu 2 means that we are considering the three time step, the current, the previous, and the next one. So these are just definitions. So you kind of want to be able to approximate Newton's law now using these definitions. So this is the original equation that we saw a couple of slides ago. And in discrete time, what you can do is to blindly apply the finite difference operators that we just introduced and maybe get lucky and have something that sort of works. So you see that the second time derivative is now approximated by the second time difference. And on the right-hand side, the identity u is now approximated by the averaging operator mu dot. And the continuous relative velocity eta is approximated by a time series eta n, which is defined as the relative discrete velocity, delta dot, minus the bow velocity. So you see that there is a direct correspondence between the continuous equation and the discrete equation. But you're able to use the discrete version in your computer in order to find the solution to your system. The question is this a good scheme? I mean, we just substituted difference operators into the equations, but we don't really know whether this scheme is actually good. What you want to do is to, again, find passivity properties. So just like the continuous case where we multiplied by the velocity and we figured that the energy was decaying over time, we can kind of do the same trick in discrete time too. So you can multiply the whole equation by the time difference and apply a bunch of identities and realize that there is a discrete energy now that evolves over time. And how does that evolve? It decreases. Okay? So we were able to essentially find a discrete energy property that mimics the energy property that we have in the continuous system. And this is a very good thing because if passivity is guaranteed, that means that this scheme is going to be stable and we're not going to run into problems when we simulate the system. But there is a second aspect which I sort of introduced a couple of slides ago, which is the question of efficiency. So the scheme that we have constructed here is surely passive, but it is probably not so efficient. And the reason is that now your update un plus 1, which is unknown, it appears as the argument of the nonlinear function phi. So you see that un plus 1 is, is found over here, that's fine, but it is also appearing inside the argument of phi. Meaning that at each time step, you actually have to solve a nonlinear algebraic equation in order to compute un plus 1. We call this kind of schemes full implicit, okay? And there aren't a lot of ways that you can tackle this problem unless you use, for example, Newton-Raphson. Is any of you familiar with the Newton-Raphson algorithm? You? Okay, well, Newton-Raphson, have a demo over here. Basically, you approximate a nonlinear function with the slope, and the algorithm is sort of guaranteed to move toward the zero. So instead of computing the zero of the nonlinear function, you're computing the zero of the line, which is obviously very easy to find. And then you can keep, approximating the zero moving along the nonlinear function, and eventually you will find the zero of the nonlinear function. But you see over here, I have plotted a tolerance. You can't really see it in class because the video is not working very well, but you can surely see it from the computer. So the tolerance essentially defines how close you are to the zero. And it is not really clear when you should stop because, the tolerant threshold sort of goes down, but when do you stop? 10 to the minus 1, 10 to the minus 3, 10 to the minus 14, you don't know. So that is an issue. And there are other issues too, like existence and uniqueness of these roots is not easily computed or easily proven, actually. And also, at each time step, these routines work at a variable cost. So sometimes you might need 4 iterations of the Newton-Raphson routine, so sometimes you may need maybe just 2. But again, variable operational cost is not great when you're trying to allocate resources in your real-time plugin, for example. So that's why I introduced the first ordering time system too, because maybe in this system there is a chance to construct faster schemes. So if you look up the literature, there are a lot of different schemes that you can use in order to integrate these equations of motion. And one such method is the midpoint method, which is described over here. And the midpoint method is a classic method, and again, you can check passivity and you find that the energy is decreasing over time, so the scheme is passive. But again, you have the problem of the update appearing inside the argument of the nonlinear function phi. So even the midpoint method in the first ordering time case is probably stable, but again, you will need Newton-Raphson in order to tackle this problem. So the question is, how can we construct schemes that not only are stable, but they're also fast? Is it possible? Well, that's what I've been trying to do in the last couple of years. So I've been developing a lot of schemes, trying to avoid Newton-Raphson entirely. And that's not an easy task in general, but luckily for the friction coefficients that we use for the bow, there is a second property that we haven't talked about yet. So the first property, is sector boundedness that we talked about a lot. So we said that eta and phi of eta have the same sign. So if you multiply eta and phi, then you'll always find a positive function. But the second property that is really, really important is that the ratio of phi and eta exists. So this function is also always well-defined. And that's a very important property, and we're going to try to exploit this property in order to construct schemes that are fast and that do not require Newton-Raphson. How do we do that? Well, we start from a very easy case now. So we're just assuming that x is now a single scalar variable, and the time evolution of x is entirely described by the nonlinear function phi of x. So like I said before, you can apply the midpoint method, but you will run into trouble because this method is fully implicit. But see what happens over here. Since phi divided by x exists, it is somehow natural to replace phi of mu plus xn with phi divided by x times mu plus x. Remember that mu plus is an approximation to the identity, so phi divided by x times mu plus x is something that is consistent with phi, So that's the trick. So you replace, instead of writing this, you write this. And now, if you expand out the operators, you see that xn plus 1 is computed using very simple operations. Just, multiplications, sums, and differences. So you don't need to do Newton-Raphson anymore because you can just compute the update in one single iteration. So that's pretty cool. The scheme is passive in the sense that, again, you have an energy that decays over time, so that's great. But how does it perform numerically? Well, okay, it is passive, it is efficient, but again, the accuracy is not probably great, because if you do a Taylor expansion of this scheme and you check how the error behaves, then you see that the truncation error is now proportional to k, meaning that this scheme is only first order accurate. Which is not great because the midpoint method is second order accurate, and so is the method that we use to integrate Newton's law. Those are both second order accurate. So the scheme that we just derived, okay, it's passive, it's fast, but it's probably not so accurate. So we kind of want to find the trick in order to make these schemes higher accurate. How do you do it? Well, you take your truncation error, you use a couple of identities, and you write the truncation error as something that is proportional to the x dt. Then you just write the finite difference approximation in the first order accurate scheme to get a second order accurate scheme. How do you do it? Like this. So you see that this correction is now appearing as a finite difference approximation in the original scheme. And you see that now this correction is proportional to delta plus x, so that in fact you can collect delta plus x and have a correction factor multiplying it. But now if you run the scheme, you know that the error is going to be proportional to k squared, so we managed to construct a scheme that is higher accurate. So in fact, you can build a whole family of these schemes basically by computing correction factors that depend on an index p, which is the order of your approximation. So we computed the first order accurate scheme, which is just one, the identity. I just showed you how to compute the second order accurate correction. But then there is no reason to stop there. You can keep Taylor expanding and you will find more and more correction factors that all depend on higher powers of k. So that's the trick. Does it work? Well, I checked it on a bunch of different nonlinear functions. So here I have like a cubic, hyperbolic tangent, hyperbolic sine, and this augmented exponential. And they ran the first order accurate, the second order accurate, the third order accurate, and the fourth order accurate schemes. And you see that in these log-log plots, the slopes actually match the expected trends. So in fact, these schemes are, they give exactly the error that you expect. But also they're all non-iterative. So we managed to build schemes that are passive, non-iterative, and where you can set the accuracy to an arbitrary order. So this is pretty great.
Can you comment on the fourth order, flattening of Platonic?
Yeah, you're reaching machine accuracy.
Okay, yeah.
You're down to 10 to the minus 15. So, we can move to the vector case basically, and nothing really changes now. The correction factors are just matrices and not scalar functions anymore, but the trick is just the same. So you add a correction factor in front of the difference operator, and then you can construct schemes with higher and higher orders of accuracy. So we can finally, run some experiments and compare a bunch of schemes and see how they behave numerically. So the first scheme is, the scheme that I presented for Newton's law is the scheme that is defined as second order in time. Then we have the midpoint rule, which is applied to the state space equation. This is also iterative and full implicit. Then we have the non-iterative schemes that I just derived here in class with you. And then I'm also comparing forward Euler, which is a very simple integrator, which is fully explicit, So it is super fast, but for which we don't really have a passivity condition. So we will see why the scheme is not very good. And here's the first example. So the top graph is a simulation of of the bow mass using a downward pressure of 100 and using a super high oversampling factor. So this is a reference solution against which I am testing all the other schemes. The 4 plots underneath are just errors. So the top plot is displacement. So that is actually the displacement of the mass. But the other 4 plots are errors. So it is the displacement of the reference solution minus the displacement of the scheme. So you see that the error of forward Euler is 10 to the minus 3, which is actually larger than the displacement. So it's a pretty big error. But then the error of the other 3 schemes are pretty much comparable, and they're down to 10 to the minus 6, meaning that the non-iterative scheme that I just derived actually behaves very solidly and it can be fully it is fully consistent with the error that comes out of the more expensive iterative schemes. But see what happens when I increase the bowing pressure. So the first case is 100, the second case is 4,000. So you see that the dynamics of the mass also changes because here we have like a proper sawtooth motion. Now, forward Euler is just exploding. This is unstable. So if you try to use that in your plugin, people will just shout at you because you will basically ruin their speakers, all of a sudden. So you don't want to use that. But then the other 3 schemes, again, have very consistent errors. This means that, forward Euler presents a clear instability and the error of the non-iterative scheme is comparable to the others. So that's pretty great. This is just a plot to show you how many iterations you need for the iterative schemes. And you see on average they take 2 to 3 iterations. That means that these schemes are 2 to 3 times more expensive to run than the non-iterative scheme that we have just derived. So it's a lot, actually. So that's pretty great. I'm going to be pretty quick on the remainder of the talk. But basically now we're moving to a more musical case. So instead of just looking at the mass, we're looking at the string now. So the Newton equation is again very similar, except that now you have a partial differential equation that describes the system. But again, you have your acceleration over here. You have the tension or the elastic force over here, which is proportional now to the second spatial derivative. But then again, you have the friction force coming from the bow. There is a bunch of different ways that you can use in order to solve this complicated system. But one useful way is to use a modal expansion. So you just assume that your displacement can be written as a sum of modes, which are just the sine functions displayed on the slide. And the modes are harmonic, meaning that you have the first mode which vibrates at omega 1, the second mode vibrates at 2 omega 1, the third mode vibrates at 3 omega 1, and so on and so forth. You can do, your modal projection. I'm not going into the detail of it, but essentially, the net result is that you can now write modal equations that only depend on time, and where you have a fully diagonal part, which is given by the linear part of your problem. But then you have a dense coupling coming from the nonlinearity due to the bow. But this system is very close to the system that we saw earlier, because instead of having just one harmonic oscillator, now we have a bunch of them that are all nonlinearly coupled via the bow. So again, you can use the same trick and write the system in first order form, and have an antisymmetrics matrix and a gradient of the energy which is just equal to the state vector. And you can use the fast non-iterative scheme in order to integrate the equations of motion. And again, you can expand out the operators, and you see that the update equation is now in the form of a very easy linear system, for which, by the way, there is a very fast inversion formula. So you don't need to run Gaussian elimination, you don't need to run any expensive like solver for the linear system. You can do this system in n operations. So it is really fast.
What, by one, you mean that there is just one line along the diagonal that's not zero?
So here, this is your update equation, yeah?
Yeah.
This is, so A is a matrix, X is a vector that is unknown, and B is a vector that is known. So in order to compute X, you need to invert A. But A turns out to be in the form of a block diagonal matrix T plus a rank 1 perturbation, A times BT, those are vectors.
Okay.
Okay. So for that, there is a very fast inversion formula. So despite the system being dense, you can use this fast inversion formula, which you can compute in ON operations. So you don't need to use Gaussian eliminations, which is ONQ, or, you know, other kinds of, I don't know, iterative linear system solves. Here you just go with this formula, and it becomes really, really fast.
That B is not the B.
No, that's bad notation. Yeah, I should change that. Thanks. And okay, the last bit of modeling that you need is to add losses and probably a bit of stiffness to your string so that it sounds a little more musical, because strings are not harmonic really. You know, you have a bit of stiffness that changes the location of the partials in the spectrum. But again, you know, you can augment the model equations, and the discrete time algorithm doesn't change. So this is just a MATLAB demo that shows you how fast this scheme is. Again, you can really see it in class because like the quality is really bad. But this is basically the simulation of a double bass. There is an oversampling factor of 4, and we are simulating the thickest bass string. So that's the worst case scenario, because that's the longest and thickest string you have, like in, you know, both instruments essentially. So you see that, well, you can't really see it here, but if you're looking at the presentation from your screen, you see that even with an oversampling factor of 4 in MATLAB, you're basically within real time. So you can run your system at 192 kilohertz, and you can still simulate that nonlinear system under real time in MATLAB. So that's pretty huge. Okay, I have some sounds here, so they can be pretty loud, so you're warned. So I have okay, these sounds are a bit rough, okay, because we're only simulating the string and the bow. There is no body modeling, there is no double polarization, there are a lot of things that are missing. So this is just exclusively the sound of friction, okay? So it is not going to be entirely realistic, but you will be able to hear that the friction model is actually pretty realistic. So focus on the friction sound and try not to bother too much with other phenomena like vibrato or body modeling. That is not modeled, that is not included. So here is the cello G2. So you can hear the friction. Yes?
What's the end there?
When you're stopping the bow.
Okay.
So the string is dissipating energy.
Yeah.
Cello C2. Okay. Double bass D2. So you can hear the friction dissipating all the energy. And double bass E1. Okay. There is another application of the bow mechanism, which I developed within Physical Audio. It's a little startup where we make plugins. So this particular instrument is called Virela, and is not strings, but bars. So So you're basically bowing bars instead of strings. And these bars are all non-linearly interconnected, but you know, the energy in the system is coming from a bow. So this is what this instrument sounds like. A different application, I guess.
It sounds like a movie. It's been used in movies?
Yeah, some people did. But okay, that's me done, so thanks for your attention. Maybe there is time for one or two questions.
Sorry for the... maybe questions first in the WebEx? Anybody? Okay. Who got that here?
I have a question, but I think I already know the answer. Using the advantage of using this kind of models in the example you just showed, is that it's lighter than having a database of samples of violin or cello, right?
Yes, it's a very different approach. So when you're sampling an instrument, you need to sample everything about the instrument. So if you're, for example, wanting to do a legato movement, then you will have to sample the legato on all the strings, on all the different combinations of legato that you want to have in your database. If you want to do a staccato, you have to do the same thing. If you want to have a note that is longer, you will have to sample it, or if you want to have like a shorter motion, you will have to sample that too. So that works great because obviously samples are 100% realistic, so it's hard to make better than samples. But then you know it can be kind of cranky to work with samples alone. You need huge libraries, so they can be pretty heavy to. Well, not anymore these days, I guess, because we have a lot of like memory available in every computer and like hard disks. But this is a different approach. So here, the memory requirements for physical models are very small. So if you make a plugin with physical models, it would weigh like 2 megabytes on your computer. So, and then you know, supposedly there is no limit to how much stuff you can simulate. Obviously, you have a limit in your CPU in this case because the physical models can be very CPU intensive. So you need to make sure, that's why you need to make sure that your schemes are running the most efficient way possible. And that's why I am developing all these fast schemes, because I am very much concerned with real-time realizations, you know, real-time like performance. But then again, you know, to add realism to physical models, you still have to simulate a lot of different phenomena. So for the bow string, here you could tell that there is no body like resonance. So that is lacking in the examples I showed you. And there are other things that are lacking, for example, gesture. These were just like open strings, okay? So that stuff can be modeled, and that's what I'm trying to do in my project now. And it takes some tinkering and some, you know, I don't know, a bit of creativity, I guess. But physical model can be pretty realistic. You just really need to be very focused and understand what is useful in the model and what is not. But the approach is the specular approach to sampling. It is completely specular. Any more questions? Is any of you into making music with plugins, computers, or music production? Oh,
I do some mix and mastering.
okay,
Not really production.
okay.
My own.
So you use Ableton or
Yeah.
Ableton? Okay. Yeah. I make reverbs as well, so maybe you're more familiar with that than like software instruments, I guess.
Can you explain how would you go about including the body of the instrument in the cello? Because it sounds quite cello-y.
Yeah, the quickest way is to measure the admittance at the bridge. Okay, so if you measure the admittance at the bridge, then you're measuring the boundary condition of your string. And that boundary condition is essentially the interconnection between the string and the body. So if you're able to measure the admittance and you're able to sort of synthesize that impulse response and include it in the boundary condition of the physical model, then automatically, when you're simulating the string, you're also simulating the effect of the body on the string.
That enters like in every time step.
But it is just literally a boundary condition. So the dynamics of the string doesn't change. What changes is what happens at the boundary. And you could go even further, because obviously the admittance is the transfer function between the string and the body. So if you know how the string is vibrating at the boundary, then you know how much force the string is exerting on the body. So you could have a model of the body where you know what the force at the bridge is, and then you could have waves developing into the body, and you could have an even more realistic simulation that way. You see?
Where like the body is just like another different nonlinear equation.
Not non-linear, it would be linear in that case, because it's just a resonator. So you could have, for example, a bank of modes coming out of a console simulation, okay? And you could use that as the model basis to do a model resonator. And then you could simulate the physics using the console modes. Yeah.
Don't you think it would be more realistic to consider like physical modeling as the boundary condition, or considering like the interconnection with the body like as a post-processing step, like as a filtering step?
Well, that's a very good question actually, and I mean you could always try to convolve the sound of the physical model with the measured impulse response, but you run into problems in the sense that if you do that, you're not simulating the right physics of the string to start with, because you're assuming very simple boundary conditions. So you're not taking into account the effect of the body. And also if you're convolving, like, what signal are you convolving? Are you convolving like the displacement of the string or the velocity? Or, and it is not clear what signal you should convolve into the impulse response of the body. Whereas if you interconnect all the subsystems together physically, then you know exactly that the signal going into the body is the force coming from the string. So that's definitely, I think, what you would have to do if you want to run a realistic physical model. Because like a lot of people just convolve like with body impulse responses, but the problem is that you don't really know what you're convolving. So it works. I mean, you will hear like an equalization of the sound, but probably that's not the sound that you're actually getting from the system. It is a different kind of sound.
Probably isn't like considering like the reliability of the state, probably like doing physical modeling in real time is more like also taking into account transients.
Yeah.
Because that difference is more efficient.
Yeah, it is true, yes. But I mean, in plugins you always have this sort of like post-processing effects, like you usually have reverbs or delays or filters. So it is not uncommon in plugins to have this sort of like post-processing bits. That's fine. But for the sake of making a physical model realistic, I would say that it is much better to either measure or model the boundary condition physically, and then have the physical boundary condition in the model so that everything runs as it should.
And just to go back to that, that would be just like the X first normal modes with an amplitude and that. Like very technical question. Like if do you have like the equation for Michele string and like how do the material parameters of the string enter?
I should share my screen again.
And this is just one dimensional.
Yes.
So there is no torsion.
No. The parameters are all here. So you have omega. These are the resonant frequencies of the modes.
Okay.
Okay. So those you can measure because you can look at the spectrum of a vibrating cello string and figure out that the modes have a certain resonant frequency. C is the damping ratios. Again, you can measure. And well, that's pretty much that. You know,
Okay.
you need frequencies and damping ratios mostly. So the material parameters in this case are disappeared. They are gone because everything has been normalized. But these are the actual parameters that you measure from like a vibrating string.
Actually, like so predicting
Those from the actual.
Yeah. Yeah.
Proposal.
What?
The proposal is with it.
Okay. Yeah. Fantastic. Cool.
I just got one more.
Yeah, sure.
Because Thomas was mentioning something about like the torsional modes and how the energy, the transversal energy dissipates into these torsional components.
Yeah, I mean, there are a lot of motions in strings. So, you know, first of all, here we only consider it like this motion.
Yeah.
But then there is another transverse wave equation, which is that. So you would have to start with, you would have to simulate the two transverse wave equations so that you have a string that moves like that, which is realistic. But then you have motion in the longitudinal direction that goes like that. And then the torsional motion as well. So they're all somehow coupled, and I don't have an answer. Like I know that longitudinal motion comes into play when the amplitude of the string is high. So when you have a geometric nonlinearity, you surely have a longitudinal motion that comes into play. But I think that for bow strings, the nonlinearity coming from the bow is so high that the nonlinearity coming from the geometric amplitude is probably negligible in a first approximation. So that is not true, for example, in the harpsichord piano, where you hear like the pitch bends coming from the geometric nonlinearity, but there you don't have like a bow, you just have like a pluck or a collision with a hammer. So you're actually able to hear the change in pitch of the partials in the transient. So you need the geometric nonlinearity in there. But for the bow, maybe you can avoid it, you know. And the torsional motion, again, sure, you have some transfer of energy there, but the speed of the torsional motion is so high that the coupling probably happens like in the kilohertz range, right? Because you have like super fast waves, you know, so the coupling necessarily takes place at like very high frequencies. And I don't know, I never simulated that, so I'm not sure. But
the contact between the bow and the string here was a point, no?
yes. Yes. Again, you know, very crude approximation. But yeah.
And just a curiosity, the Rosin, how do you model like when you're experiments? You play, you have to put again, like how is there a time dependence of the friction coefficient associated with the Rosin?
Associated with?
With the age of the Rosin.
Oh, well, no, it's not time dependent. You know, like this model only depends on the relative velocity. Okay. But then there are other models that include, for example, the thermal properties of the rosin. So because the rosin heats up and cools down over a cycle, then you can include the thermal component in that and have a more complicated friction coefficient that not only depends on relative velocity, but also depends on temperature. Again, you know, all sorts of, it is a very complicated problem. Nobody knows what the real answer is.
But you keep on adding like the terms in the equation.
You keep adding, yeah, more complicated. But it is not too complicated, but it can get a little bit expensive. And maybe for the purpose of sound synthesis, maybe sometimes you can neglect some effects and hope to get like a relatively realistic sound. So I think that for bowing, really what you need is a very good modeling of the body. And because the body harmonics are really, really important. And maybe the attack as well is important, so you kind of want to nail that. But then, you know, the steady bow motion, I think you can do with very few ingredients, you know.
Fine. The normal modes of the bow itself.
Oh, like as if the bow was a distributed system.
Yes.
Like a bar or something. Or
There's
like
a extra bar that also vibrates.
Sure, yeah. That you can do. Sure, definitely. It is definitely possible. And it wouldn't be too complicated, I don't think. It's just like a cable sliding across another cable. It's just two equations, you know? It is definitely doable, yeah. Collide and also intermittent contact. So sometimes, you know, it sticks, but maybe sometimes it will, I don't know, jump off. So, I mean, whatever you want to do, like, you just tell me, you know, can probably write down a model and like simulate it, you know. Okay, so, definitely possible.
Thanks a lot.
Thank you, guys.
Thank you.